We now take our discussion to RLC circuits. To begin with, we are considering parallel RLC circuit, which is source free. That is, there is no source, DC source present in the circuit, and since we need energy, so we assume that uh, the energy storing elements, one or both of them, are going to have some initial energy in them. So we have a parallel configuration of an RLC circuit, and we are assuming that there is some initial energy present in the circuit. So let us assume this inductor has some current already present in it, and we are interested in finding the voltage across each element. In parallel, it is going to be same. So we are assuming that the initial current through the inductor is some value as shown in the direction shown, and we have to find the response. By response we mean to find an expression for Vt. So if we start with the same analysis that we developed for RL and RC circuits, we have to come up with a differential equation. So the first step is to come up with a differential equation, and for a parallel configuration we can use node voltage to come up with an expression. So if we write the equation for this node, we are going to come up with an expression like V minus 0 over R. Remember, V is a function of time, Vt, plus what would be the current in this direction would be plus 1 over L integral 0 plus 2t of V dt plus the current at this point. But if we want to mark this current in this direction, that would be opposite from the direction of this current. We are going to put a negative sign here, minus I 0 plus. In the downward direction it would have been positive current, but we know that I naught is flowing in the reverse direction, so it is minus I naught plus the capacitor current through the capacitor, that is C dV by dt is equal to 0. Now this is an integral differential equation, it's not a differential equation. So how to convert this to the purely differential equation? We take the derivative of V with respect to time throughout, and we are going to get 1 over R dV by dt plus 1 over L V, this is a constant, the derivative is going to be 0, plus C, it's already a derivative term, so we are going to get a second derivative of this term here. Now this is a differential equation, but it is a second order differential equation. I am very sure you might have covered this, solving this equation in your differential equation course. So I can skip the solution, but how to solve this one, but it is very important to understand in the context of circuits. So I am going to take some time here and solve this step by step. So how to solve this? From our knowledge of the solution of a single order or first order differential equation from RL and RC circuits, we know we had several methods there. We can directly solve it, we can assume a solution, and then we can solve it. So from our intuition and some experience from RL and RC circuits, let us come up with the solution, and then to try to find the unknown quantities in the solution. So what would be something, there is a very important thing to note about this equation, that we have the derivative of v itself, and the second derivative of v adding together to get 0. So it means that the form of v should be such that its original form, its derivative, and its second derivative must be of the same type. Otherwise, how can they add together? So remember, things of the same kind add together. So v should be such a thing that itself, its derivative, and its second derivative must be of the same kind. What can it be? So suppose we assume this is the solution. No, we are assuming solution to be Vt is equal to a some constant e raised to the power s some constant t. Now s is a constant, a is a constant, and in order to get a very general thing, let us assume that a and s can be complex quantities as well. Complex numbers. I hope you remember the complex numbers. So if z is a complex number, then it has a real part and it has a imaginary part. In electrical engineering, we use j, for small j, for iota, because I will confuse with current. And there is another way of writing this, although we are not going to concern ourselves with that form of notation in this course. But you already know that a complex number can be written by a magnitude and an angle. So this is the polar form, and this is the rectangular form. For this course, the rectangular form will suffice. And remember, this polar form is basically of this kind. R is a constant, e raised power iota theta. This is the polar form of a complex number. So a and s can be real, can be complex. We will see to that later on. What is more important is this function, the exponent e function. So we know that the derivative of ex is ex, and if we keep on taking derivative, the form remains the same. If we have a constant here, the constant will remain here. If you have a constant here, it comes here. The coefficient changes here, but the form of the function remains the same. So we needed something, and we are assuming that the exponential function is that thing. And if this is a solution to this equation, it must satisfy it. So if we put this solution in that equation, we are going to get 1 over r. And what is the derivative of this thing? As e raised power st plus a e raised power st v itself over L plus c, and the second derivative is going to be a s square e raised power st equal to 0. So if this is the solution of this, as we are assuming, it must satisfy itself in this equation. So we can write it by taking terms constant a, so sorry, s is not constant, a e raised power st. So what we are left with is s over r plus 1 over L plus s square with the c equal to 0. So for this whole thing to be 0, either a is 0, e raised power st is 0, or this whole thing is 0. Now these two cannot be 0, because if these two are 0, then we are assuming v is 0. Although v0 as satisfies this, but then everything becomes 0, and the initial conditions are not justified. So if v is 0 here, this term is 0, this is 0, this is 0. So how can a non-zero thing be equal to 0? So these cannot be 0, because this is a trivial solution and we are not considering that. What we are left with is this, the auxiliary equation, or commonly known as the characteristic equation. So in solving this characteristic equation, we are going to come up with two values of S, because this is a quadratic equation. This quadratic equation can be solved, and we are going to get two values of S. Let us call them S1 and S2. And S1 would be, if you solve it, which I am not going to do because you should be able to do it yourself, 1 over minus 1 over 2 RC plus square root 1 over 2 RC square minus 1 over LC, and this will be something like this. Here we have a positive, here we have a negative, all else is same. Now these are two values of S, and if we use any of these, this equation, and this is the solution, this satisfies. So what we are trying to say is V1, this voltage, either it is equal to A e raised power S1t is also a solution. It will satisfy without issue. And V equal to A e raised power S2t, this is also a solution. Both are valid solutions. So in a particular case, we know only one solution will exist. So a voltage cannot be two things at the same time. It must be one thing. So it means that we cannot take just one form of solution and then say, okay, this is the solution. So we need something else. So if we put this in this equation, obviously, this one, the differential equation, we are going to get a solution. And if we put this in it as well, we are going to get the solution as well. So putting this, we are going to get all this the sum equal to 0. If we put this, we get the sum of these three terms equal to 0. What if we put this? What if we add these two together and just for generality assume that this is a different constant, this is a different constant. So I've taken them as A1 and A2. If we put only this one into this equation, what we get? 0. If we put this one into the equation, we get 0. So if we put the sum of this, linearity wins, we are still going to get 0. So it means that this too is the solution of this second order differential equation. It means that assuming the solution to be of this kind is not very general, but assuming that this is the solution is more general. And this is what we are going to do. Now, there are a few observations here, that we know that exponent of something in equations must be dimensionless. So S1t must be dimensionless, S2t must be dimensionless. We know the dimensions of t are second. So the dimension of S1 must be 1 over second per second. So 1 over second into second is a dimensionless quantity. So it means that S1 and S2, these things are going to be termed as frequencies because of their dimension. So we are going to call them frequencies, and we call them as complex frequencies because sometimes they are real values, but sometimes they are complex imaginary terms. They have they are complex quantities. And similarly, this A1 and A2 are going to have dimensions of this type because this term is a dimensionless term. So this A1 must have the same dimension as V. A2 must have the same dimension as V. So this is very important to note. And from this equations, from the solution that S1 is of this type and S2 is of this type, we also understand that if S1 has a dimension of per second, this is a frequency. Now you see this term is being added to this term. So this term must also be a frequency must be termed frequency, and this term must be frequency. Now this is square root of something, so if you ignore this square, so 1 over 2 RC is a frequency, but 1 over under root or square root LC must be a frequency as well. So 1 over 2 RC must be a frequency term as well, and we have used a symbol alpha to represent this. And 1 over square root LC is also a term, omega 0 or omega naught, and we 0 or omega naught, and we call this the resonant frequency. And this is something that is known as exponential damping coefficient, or sometimes also called as neper frequency. The resonant frequency, the neper frequency, and what they really are, do they signify? These are just symbols used for these terms. This will be clear later on, inshallah. So it means that S1 is equal to minus alpha plus square root alpha square minus omega 0 square, and this is equal to minus alpha minus square root alpha square minus omega naught square. So we have just plus minus here. So sometimes we say that S is equal to minus alpha plus minus square root alpha square minus omega naught square. It does not matter which one do we call S1, which one do we call S2. One of them is S1, one of them is S2. So ultimately we come up to this thing, that V, the solution to this second order differential equation would be V A1 e raised power S1 t plus A2 e raised power S2t, where S1 is equal to this thing with the plus sign, S2 is this thing with the negative sign, and in S1 and S2 this alpha is equal to 1 over 2 RC. Remember, this is circuit specific. For other circuits this may be different. We are going to see that later on, and omega 0 would be 1 over under root LC. So this is the solution that we had been looking at. Now if you look at the solution, depending upon this term, we are going to have three cases. One, if alpha square is greater than omega 0 square. So what will happen? If this term is greater and this is smaller, this whole thing is going to be larger than 0, positive term, and square root will be a real value, and S1 and S2 would be real and distinct. In such a case, we call the response to be overdamped. When this is the case, we say that the response is overdamped. The other case is when alpha square is less than omega naught square. In such a case, this would be an imaginary term with iota, and S1 and S2 would be complex numbers. So with this term same, so complex conjugates. So S1 and S2 would be complex conjugates. When this happens, we say the response is underdamped. And then there is the third term. We don't have space downward here. I'm writing it here. In the third case, then alpha square is equal to omega 0 square. If this term is 0, because they are equal, or S1 will be minus alpha, S2 will be minus alpha. So S1 and S2 would be real. Here we had distinct separate values, here real and equal. And the response is said to be critically damped. We would later see there is a fourth case, although it's not discussed. But if alpha in a circuit is 0, if alpha is 0, this is a case of undamped response. Exponential damping coefficient, alpha is called exponential damping coefficient, so there is no damping, undamped response. In the next videos we are going to continue.